So looking at trig in 3 dimensions rather than 2 dimensions. 2 dimensions is really easy to work with because you see the triangle and there you go. Sometimes it's hard to see the triangles in 3 dimensions because of the drawings, the way they're drawn. Sometimes it's easier just to redraw all the faces of the shapes in 2 dimensions so you can see exactly what you're doing. Maybe you want to draw some extra triangles that aren't actually in the original diagram but may be useful to use. There's a couple of main questions really. Finding the angle between a line and a plane. So a flat surface and a line. So we use this as an example. This cone has a diameter of 18 centimetres. We know the slant height of the cone is 15. We want to find the angle the curved surface area makes with the base. So this is an example of a line and a plane. The base would be a plane. Now, as far as the curved surface area, we're just going to look at, say, what looks like the edge in our picture. So it's a line with the plane. How do we create the triangle in this situation? For any point on the line you want, it doesn't matter where, you drop a perpendicular. But it makes sense to drop it from where you know the length of the shape. So in this case, I'll drop it from the vertex because I know the length of that line is 15. And we drop it down. And then we join that point of intersection to the point where the line meets the plane. And in our diagram, that's already there for us because, of course, that is the diameter of the circle. So we now have a triangle. The base will be 9. Theta that I've labelled in there is the angle we're finding, and it becomes a very simple trig problem. Cosine theta is 9 on 15. We get 53 degrees. Sometimes we have to find the angle between 2 planes. So 2 flat surfaces. So this one's a little bit more interesting. ABCD is a tetrahedron and the length of each side is A. Find the angle between 2 adjacent faces. So the faces are planes, the angle that they meet. From a point on the line of intersection of the 2 planes, because 2 planes will meet at a line. So from any point there you like, draw perpendiculars from that point along the plane. Now I've chosen that point E, and to make life easy for myself for measurements, I've chosen the point where that line would go through the vertex. But because this is a tetrahedron and everything's nice and symmetric, when I go along the base, that plane, it will also go through D. It has to through symmetry. So I have now created a triangle. There's the angle that I have to find. It's angle AED. Maybe it is easier to redraw this one. And so there it is, AED. All I know at this stage is AD has length A. So I'm going to draw another triangle. There's the base. What do I know about the base? Well, it's a tetrahedron, so I know that angle's 60 degrees. And again, I know AC is A. I could find AE, which is a side that is in my other shape as well. So that could be handy to find that side. So let's find it. It's an exact value. So it would be A root 3 on 2. I didn't actually use trig, to be honest. I used the exact value because I know a 30-60 triangle has sides always in the ratio 1, 2, root 3. Well, A is on the side that would represent 2 in that ratio. Therefore, AE must be root 3 on 2 times A. You could, of course, use trig to find it. I'm actually going to need the cosine rule to solve this problem now because I've got 2 sides in that triangle and I want to find an angle. It would end up being this beautiful expression. 3a squared on 4 plus 3a squared on 4 minus a squared over 2 times a root 3 on 2 times a root 3 on 2. Lovely thing about that is actually the a squareds all cancel and I come up with a definite number. Turns out to be a third. So cos theta is a third, so that angle is 70 degrees, 32 minutes. Here's an HSC one. And as I was saying, it actually used to be in the Extension 1 course. So a surveyor is at point A. We're told it's due south of a tower. They've said height H. They've given us the angle of elevation of the tower. The surveyor then walks 100 metres due east and has another look at the tower, but now the angle of elevation is 30 degrees. Express the length of OB in terms of H. Okay, I'm going to draw a triangle that includes those things, and triangle TOB would have height H. And we know that angle's 30 degrees. That was the angle of elevation. So an expression for OB over H is tan 60, so I get H tan 60. There is my expression. I suppose I could rewrite that as root 3h, because we know what tan 60 is. Show that H is 50 root 2. Okay, I need another triangle. This time I'm using the angle of elevation of 45 degrees. Is that one? ATO. And it is, of course, our 45-degree right-angled triangle, which I know is isosceles. So therefore, AO must be equal to the height of the triangle. Now, in triangle AOB, that's where this becomes handy, because I now have a triangle where I know AB is 100, OA we've just established is H, and in the last question we established OB was H tan 60. Bit of Pythagoras should get us our result. Play around with that. Eventually, there it is. H is 50 root 2. Part 3 then. Calculate the bearing of B from the base of the tower. So now I will draw the ground. The compass is at the point O. We want the bearing to the point B, and I've added in the dimensions that we've found. There's 50 root 2 and 100. That is the angle I wish to find, angle NOB. Well, I'll find angle AOB, because that's in that nice little right angle triangle down the bottom. Tan of that is 100 over 50 root 2. We get 54 degrees 44. So to find the bearing, we subtract it from 180, and there we go, 125, 16. So we will add 6C to our list of questions.